Well, hello, ladies and gentlemen. We are going to be moving on from superheated vapor, the saturation dome, going to be moving on to what's called ideal gas behavior. We're going to be looking at a simple expression relating pressure, volume, and temperature for a gas. In other words, the ideal gas behavior that I've been talking about here. We're also going to look at a quantity called the compressibility factor Z. Compressibility factor Z, we're going to look at what's called the compressibility chart. And then we're going to deal with cases where the compressibility factor is approximately equal to 1. And in that case, there's a very simple relationship relating pressure, temperature, and volume for a gas. And then we'll do an example today. So why don't we get started here by kind of reviewing what we did for the last couple of days very quickly. So we have temperature, specific volume, we have the saturation dome. Here is an isobar. So here we have super cooled liquid, SCL. And then here we have saturated mix inside the dome, saturated liquid, saturated vapor on either side of the dome. And then out in here, we have superheated vapor, okay? Now, what we finished off last time was to get properties of a superheated vapor, we use what are called superheated vapor tables. Sometimes they're called steam tables if we're dealing with H2O. So we use superheated vapor tables. And I think I showed you this last time. So let's have a quick look at a superheated vapor table out of the text. So this is a saturation table for H2O. B4. Superheated vapor table for H2O. Pressure, temperature, specific volume, internal energy, enthalpy, entropy. So you can, if you give me a pressure and you give me a temperature, I can presumably go to a superheated vapor table out of the notes or the textbook and extract out the various properties, okay? So that's one way. So let's say we're interested in getting a specific volume for a given pressure and temperature. Well, we would obviously use a table. We may have to do a little interpolation between temperature or pressure points in order to estimate a specific volume, for example, okay? So we would get properties from tables, superheated vapor tables, out in the superheated vapor region. So that's how we would get properties. Now, let me show you another way of getting some properties in the superheated vapor region. So if we have a superheated vapor, we can also use what's called the compressibility factor. Z is the compressibility factor, and it's equal to the following quantity. Pressure times volume divided by mass times the gas constant T multiplied by temperature. So if we have a container, let's say, and it's a gas, it has a pressure, it has a temperature, there's a certain amount of mass in it, and it has a volume. Pressure, volume, temperature, and mass are all related by this equation here. Z is some quantity that's looked up using some kind of a table or a chart. And Z, the compressibility factor, is equal to pressure times volume divided by mass times the gas constant times temperature. Now, hopefully you've heard from physics of the ideal gas law. We're getting to that right here. If you remember, If you set Z equal to 1 and you have all this quantity equal to 1, then you have what's called the ideal gas law. We're going to get to that in just a moment. Okay, so if we have a superheated vapor, we can use the compressibility factor to relate pressure, volume, temperature, and mass for a gaseous material. First of all, before we start using any of this, I do want to point out what this R is, okay? And actually, before we do that, I want to show you there are two versions of this equation. There's pressure times volume. In this one, I have a mass times a gas constant times a temperature. We also have the number of moles, N, times a universal gas constant, T, times temperature. So we have two different versions here. One involving the mass and one involving moles, okay? Number of moles or molecules. So we could have N moles inside of our container of gas as well, okay? So in both of these equations, we have this R term here. One's a little bit different. The first one, so what is R? R is equal to the gas constant. Gas constant. It is material specific, and it has units of energy per kilogram, or energy per unit mass, per degree temperature. In metric, it would be, let's say, a kilojoule, or a joule, let's say, per kilogram, degree in Kelvin, okay? That's what it would be in metric. Okay, so R is the gas constant and is materially dependent. RU is the universal gas constant. Universal gas constant, i.e. U for universal. Universal gas constant, that is a constant which is not materially dependent and is valid for all gases. So this guy has units of energy per mole per degree. If this were in metric, it would be joule. Well, it could be kilojoule per kilomole. Kilojoule per kilomole, degree in Kelvin. If it's a metric, then that's the unit the universal gas constant would take. All right? The value of the universal gas constant, by the way, running out of space here. The value of the universal gas constant, RU, RU is equal to 8.314 kilojoules per kilomole degree in Kelvin, okay? So 8.314 kilojoule per kilomole degree in Kelvin. That's the actual physical value of the universal gas constant. Now, let's say we have a material and we want to go from the universal gas constant and calculate the gas constant for a certain material. We want to start off with the universal gas constant, which has moles in the denominator, and we want to go to the gas constant, which is materially dependent and has mass in the denominator. Well, how do we go from moles to mass? We have to use a molecular weight. So note, the gas constant R for a particular material is equal to the universal gas constant divided by the molecular weight of the material. Let's make sure this works here. Let's look at the units here. I have energy per mole degree in Kelvin. I'm sorry, per degree. And then in the denominator, I have mass per mole. The moles cancel out, and I get energy per unit mass per degree. Okay? So, to get the gas constant, take the universal gas constant, 8.314, and divide it by the molecular weight of the material. And we'll do an example involving this as soon as we get through the material today, okay? Okay, so let's go back to this compressibility factor here. Let's go back to this compressibility factor. Now that we know what the gas constant and the universal gas constant are, you've encountered this stuff before, but let's make sure we're all on the same page. So again, let's write the expression for the gas constant, Z. So for a superheated vapor, pressure, volume, and temperature can be related according to the definition of the gas constant. I'm sorry, compressibility factor. Z is equal to PV over mRT. And I can also write this as pressure times volume is equal to nRUT. Okay? Just talked about the universal versus the gas constant. Okay, we can go between one and the other. You give me the material, I can calculate R from RU with the molecular weight. Okay? Now, let's look at how the compressibility factor is determined. Let's say we have a pressure and a temperature, and we got a material and a certain amount of mass, and I want to know what the volume is or something. I want to use this equation. How do I get Z? How do I get Z so I can relate pressure, volume, temperature, and mass? Well, you've got what's called the compressibility chart. Compressibility chart. Compressibility chart. What the compressibility chart is the following. It is Z on the y-axis, the compressibility factor, a quantity called the reduced pressure, P-R-E-D-U-E-C-D, reduced, P reduced or P-R-E-D, P reduced pressure, and then curves of constant reduced temperature. T reduced. Okay? So I'll tell you what reduced means in just a moment. But what we have here is basically Z, the compressibility factor, as a function of temperature and pressure. That's basically what this chart will give us. You give me a temperature and a pressure, and I can look up the compressibility factor Z. Now, if you go to the text here, let's have a look here. Let's have a look at the text. Let's go to the textbook here. I'm sorry, the notes. Here we are. If you go look at page 28 out of the notes, here's the compressibility factor right here. You see on the y-axis we have Z, which is a function of pressure. This is specific volume right here, so that's volume divided by mass. That's why there's no mass in that equation. So it's a compressibility factor, which ranges from 0.2 up to about 1.2. Then we have reduced pressure on the x-axis, and then we have, as you can see, curves of constant reduced temperature. I'm using P sub R here in this plot, and T sub R to indicate reduced temperature and pressure. Okay? Now, one thing to notice here, if Z is approximately equal to 1, the compressibility factor, If Z is approximately equal to 1, then this expression here, this relationship between temperature, pressure, mass of a gas becomes very simple. We get pressure times volume is equal to mass times the gas constant times temperature. If Z is equal to 1, or approximately equal to 1, you can put approximately here if you want, then I get PV is equal to MRT, okay? I also have PV is equal to NRUT, okay? If Z is approximately equal to 1. These two equations right here, these two equations are referred to as the ideal gas law. Oops, damn it, did it again. So here, if Z is approximately equal to 1, and that means this is 1 right here, then PV over MRT is equal to 1, and PV over NRUT is equal to 1. And then we get PV is equal to MRT, and PV is equal to NRUT. These two equations right here, under the simplified case where Z is approximately equal to 1, these guys are called the ideal gas law. Ideal gas law. Put a box around them. Okay, these are the ideal gas law. Hopefully you've dealt with these before in basic physics. Well, you're going to be dealing with it now, okay? Ideal gas law. That's when Z is approximately equal to 1. So when Z is approximately equal to 1, when we have a good temperature and pressure range in which Z is 1, or nearly so, then the relationship between pressure, volume, temperature, and mass becomes very simple. And we can calculate properties for superheated vapor with relative ease if Z is approximately equal to 1, okay? Now let's figure out where Z is approximately equal to 1, under what conditions. First of all, let's define what we mean by reduced pressure and temperature. What are these things? Well, T reduced, I'm just going to write TRED, and I'm going to get rid of this. Reduced, you can leave it. I'm just going to put a reduce there. T reduced is defined to be equal to the temperature of the gas divided by the critical temperature. The critical temperature, okay? And P reduced is equal to the pressure of the gas divided by the critical pressure. Now, these should be kind of familiar with you. Let's remind ourselves what these critical temperatures and pressures are. Let's go back to the saturation dome. Let's go back to the saturation dome. Let's go back to the saturation dome. So here's our saturation dome. Temperature, specific volume. Here's the dome. The peak temperature in the dome, the peak temperature on the top of the dome is equal to the critical temperature. This is the critical point. Critical point. So the critical temperature is the peak temperature in the dome. And there's also an isobar that goes through right through the very top of the dome. So this is the P critical isobar, okay? And if you recall, where do we get these critical temperatures and pressures? Let's have a look. So we got our superheated vapor table, saturation pressure, saturation temperature. Very first table, B1. Chemicals, chemical formula, molecular weight. This is going to be useful here soon when we do some stuff with the ideal gas law. Critical temperature in Kelvin and critical pressure in bar for various materials. Okay? So critical temperatures and pressures are out of table B1. So T crit and P crit out of tables B1, okay? In the notes. Okay, let's figure out where the ideal gas law can be used. Where is the compressibility factor approximately equal to 1? That's the next question we have. When can we use this ideal gas law, Z is approximately equal to 1? Makes our life so much easier if we can assume this relationship between pressure, temperature, volume, and mass, okay? Well, let's have a look at the compressibility chart here. So the point is Z is 1 right here, okay? So along this horizontal line, Z is approximately equal to 1, okay? Now let's look at reduced pressure first. So here we have a reduced pressure of 0.5. Here we have a reduced pressure of about 0.25 right in the middle. 0.2 is a little bit closer here. And we can see that all these curves of constant reduced temperature indicate a reduced pressure, a compressibility factor Z starts to collapse towards 1 as reduced pressure goes to 0. So as reduced pressure goes to 0 and we go from left to right on the x-axis, the reduced pressure axis, the Z factor curves, the compressibility factor curves, all collapse to 1. So the first thing we can think of is as reduced pressure goes to 0 or gets very low, Z goes to 1. So that's the first thing to say. So the first thing to notice is, as the compressibility factor Z as the reduced pressure goes to 0, P reduce goes to 0, Z becomes approximately equal to 1, okay? So as we move this way on the chart, for any reduced temperature, Z approaches 1, okay? Now let's go back to the compressibility chart. So low reduced pressure means that we can use the ideal gas law. Z is approximately equal to 1. What about temperature? Well, certainly for fairly low temperatures or fairly low reduced temperatures, so here's reduced temperature equal to 1, Z starts to vary very quickly as reduced pressure increases. So Z actually goes down to 0.2 for a reduced temperature of 1 at just 1 PR equal to 1, okay? So for low reduced temperature, Z varies very quickly with reduced pressure. So we don't want a reduced temperature that's too low. We want a reduced temperature that places us somewhere in here in the compressibility chart, okay? Now we can go up and reduce temperatures, 1.4, 1.5. Here's 2 right here, 2. So if we have a reduced temperature of, let's say, no less than 2, then we're on this curve or above this curve, and we have sufficiently low reduced pressure, let's say less than 0.2, then we end up in a small envelope right in here on the compressibility chart, very small envelope, and Z is approximately equal to 1. So I'm going to make the claim here. I'm going to make the claim for T reduced greater than 2, and P reduced less than 0.2, the compressibility factor Z is approximately equal to 1. That puts us basically, let me put in a few more reduced temperature curves. So this is T reduced equals 2 right here. So using this rule here, we end up staying right in this region where Z is approximately equal to 1. Okay, Z is 1 right there. Okay, so let's put a little box around that. I'm going to write it again. In fact, I'm going to write it right over here on the other board so we can clear up the clutter. So let me write the definition of the compressibility factor, and then write the ideal gas law, and then indicate the conditions under which we can use the ideal gas law. So Z is equal to PV over M RT, which is also equal to PV over N RUT. And for reduced pressure less than 0.2 and reduced temperature greater than 2, Z is approximately equal to 1. And these equations here imply PV is equal to M RT or N RUT. Okay? So why don't you write this in your notes somewhere? This is a very important set of information, and these equations pretty much encapsulate what we've gone over the last 20 minutes or so. Okay? Definition of the compressibility factor Z. Z is a function of temperature and pressure. Under certain ranges of temperature and pressure or reduced temperature and pressure, we can say Z is approximately equal to 1, and then we get the ideal gas law, okay? This is the ideal gas law. PV is equal to MRT, or PV is equal to NRUT, ideal gas law, all right? Okay, let's do a nice example involving a superheated vapor, and we're going to use the compressibility factor, and we're going to use the ideal gas law, and we're going to compare the values that we get using tables versus the compressibility chart versus the ideal gas law. So we can see how to hit a particular problem from all sides using these relationships. Okay? Let me pause this for a second.